The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2, 1.
Welcome, everybody, to the Into the Impossible podcast, production of the Arthur C. Clarke Center for Human Imagination in the Division of Physical Sciences at UC San Diego. And it's a treat to welcome Sir Roger Penrose back to UC San Diego.
Pleasure, certainly, yes.
Yeah, we're certainly
great to be back.
Thank you. We're extracting a lot out of you in this visit. We are grateful to you for be hosting these many talks that you're giving. You gave one talk that was more than standing room only earlier today. You're doing this interview now, and tomorrow you're giving another talk. It's really quite generous of you. Thank you so much. And I've come to expect that of you. You're gracious as always and so responsive, and it couldn't be a greater treat to have you affiliated with our fine university. When I was mentioning to some of my followers online that you were coming, I wanted to highlight that this is actually the 5th decade of this book here, The Emperor's New Mind, which is, as I pointed out, was the first popular, so to speak, science book that I ever read as a teenager in 1989 when it first came out. Mm-hmm. And I've been remarking along with my friends on how much has changed, but also how little has changed. And I thought we'd take this opportunity on the 5th decade of its existence on planet Earth to kind of review some of the discoveries that you've had and that science has progressed since the writing of the book. I know it had a second edition and other editions since this first edition that I have here, but I wanted to get a general impression from you. Did this book exceed your expectations? Did it sort of touch a nerve in the popular consciousness that it's still a bestseller to this very day for you?
I'm not sure. I initially thought that it might either disappear without trace or that maybe there would be a little attention to paid to it. Well, it was round about the same time as Stephen Hawking had written his book,
yes,
A Brief History of Time. Mm-hmm. And I remember asking or noting that his book had a foreword written by science presenter
Carl Sagan.
Yes,
that's right.
Carl
Yes.
Sagan.
Mm-hmm.
Yes. And so I thought, well, I better try and do something that. And the best I could do, I thought I happened to know Martin Gardner, so
right.
So I thought if he wrote a decent foreword, or if he was prepared to do it. First of all, I wasn't at all sure whether he'd be shocked by the point of view I was presenting.
Right.
In fact, he was very favorable expressed. He said he rather thought of things the same way, mm-hmm. and he wrote a very nice foreword. And then I thought, well, perhaps it won't disappear without trace. At least some people will read it. Mm-hmm. I was very naive, and I didn't expect this sort of mixed is the wrong word. There was a lot of antagonism mm-hmm. from certain quarters. Mm-hmm. I mean, I expected there might be people who would object to what I'd written from the artificial intelligence community because I was trying to say there was a bit more than computation going on in human thinking. And also that I might have trouble with the religious community because I was certainly not expressing a religious view, and I was trying to go against that somewhat. Well, not general religious, but somehow that there was something outside science which had to explain our conscious beings and so on. What I hadn't expected was a lot of philosophers objected to what I was saying too. I think they just thought I was too sloppy. Mm-hmm. I was sort of expecting that there would be a lot of young people picking up on the ideas and maybe writing to me or something. My initial experience was nothing of the sort. They were only old retired people who wrote to me. And they were old retired people who'd had time to read the book, I guess. And amongst the people, not just the retired older, and a few young people there were, usually people who got inspired by the book. One in particular who became there was a man named Michael Wills who he was intending to have a series of television programs based on the book. It ended up being one program, mm-hmm. but he had, as a researcher, somebody who was doing the work, and then he sort of gave up half the way through, and I thought maybe they'd had a row or something. Mm-hmm. And he said, well, actually, he'd become interested in something else. And he actually turned out, he became a singer, and he became the leading singer in Britain.
Really?
Tenor singer, yes.
Really?
So I didn't mind him. He was like one of the few people as a youngster who had written to me about the book. So
Well, that's a decent excuse to.
yes, but one of the main things that I guess was a positive aspect of this was that Stuart Hameroff read my book.
Right.
And he more or less wrote to me to say, well, the one thing that seems to be missing from your point of view was these things called microtubules. You see, I'd written the book feeling, quite... I knew a bit about physics and mathematics, and I would try and learn a bit about neurophysiology, and maybe I'll find enough about it to see where my ideas had any relevance to that. And I got to the end, and I came to the conclusion I didn't see any relevance, mainly that nerve propagation. You see, I need to preserve some kind of quantum coherence. And I just learned that nerve propagation there's no hope. That the signals, there's always big electric fields which would decohere, all your quantum coherence get lost in the rest of the brain, and it was completely hopeless. So I sort of had a rather feeble ending, which I didn't really believe in myself. But Stuart wrote to me and said, I think the key thing you're missing is these things called microtubules. Now, I'd never heard of microtubules, and I get lots of letters and emails didn't exist in those days, but letters from people, crackpots of one kind or another. So I thought, oh, here's another, you see. And then I thought, these things, look, he's got a picture of these things. It looks like they must be real. So I look at them up and I say, yeah, they're real, all right. And it seemed to me these were structures far more probable, plausible things which could preserve quantum coherence. I mean, it's still a challenge, a major challenge. But the fact that they were tubes and the fact that they were symmetrical in various ways, and it looked to me there was a much better chance there. So it sort of started a collaboration with Stuart, and we formulated this general point of view called orchestrated objective reduction. Objective reduction is something I treated in the book. But although that's one of the things I think the exact form I had was not correct. There are a few things I would say were wrong in the book, but not majorly wrong. That is to say, it wasn't the right criterion, but it was the sort of idea which I still believe in, namely that it's gravitation, which is the place you have to look for where quantum mechanics, it needs something to make it consistent. The theory we have at the moment is a combination of two things which mutually contradict each other. And people sort of live with that and try to live with it and make sense of it. But they don't normally take the view there's something wrong, which was the view I took and which I still hold. And it's really the second book, which was Shadows of the Mind, where I more or less, I introduced the microtubules there and the point of view which I still believe in with regard to how to fix up quantum mechanics.
And that the microtubules have sort of a geometric connection to them, or sort of a natural geometry to them, is no surprise that appeals to your deep love of geometry. But is there something deeper to it other than just their geometric structure?
Well, I think there is. Although it's not been made use of very much in the later developments. I mean, it's already there. That is, these structures that are... Well, actually, microtubules come in two forms. They're two different lattices. I didn't know that at the time. One of them are what's called the A lattice, which is highly symmetrical. And the other is the B lattice, which is not quite so symmetrical. It's got a seam down one edge along the tube. Whereas the ones which are highly symmetrical seem to me have a much better prospect of preserving quantum coherence. So you want quantum effects to be preserved at a big level. And symmetry is a good way to do that. So when you say the geometrical structure, that's part of it which is appealing to me. And there's this thing called the Jahn-Teller effect. This is when you have a highly symmetrical structure. Well, maybe it could be a crystal-like thing, or it could be like a tube with different kinds of symmetries. And the high symmetry means that you can have, well, there's a sort of lowest level of activity, which is the sort of lowest quantum level, and that is what's called degenerate. So you have information at that level, what's called quantum information at that level, which is shielded from the next level. So there's a big gap between that level and the next. And you get that when you have very symmetrical structures. And the
It's a band
microtubules,
gap, like a band gap. Yeah.
yes, a band gap. Microtubules, I mean, there's a lot of other problems which it simply doesn't resolve just like that. But it seemed to me there was a lot of much more promise in microtubules than anything else I'd seen before in neurophysiology.
So one thing that distinguishes your research, it's not without its speculations and new and novel ideas, but that in almost every case that I've found in your research, you predict effects which are in principle possible to prove wrong. In other words, they are possible to be falsified.
Yeah.
To date, you've enjoyed success in that they haven't been false. Many things have not been falsified, and in fact, many of your discoveries have stood this test of time and test of other experimental and mathematical scrutiny. Is that something that's important to you? Obviously, you know of and our listeners will know of Karl Popper, and his sort of objectivist and how do we determine if something is scientific? Well, it must be falsifiable. And I always point out that I believe, and you talk about Gödel and his incompleteness theorem very frequently in The Emperor's New Mind. But I feel like physicists almost have an envy of Gödel's incompleteness theorem, in that we have no way of objectively showing that our assumptions are built upon perhaps incompatible premises or unprovable or unfalsifiable axioms. And I wonder, to what extent are you guided by Popper and the falsification demarcation theory? Is that something that's important to you? Would you work on something that is not? Because it could be tomorrow our colleagues find that microtubules are just impossible to be, they can't maintain coherence beyond, nanosecond level timescale, something like that.
Well, you see, I think your point is well taken. But there is a major part of what I've done in relation to physics and how it relates to mathematics, which at least as yet has not been falsifiable. Yeah. And, I rather regret the fact that it's not. This is the theory which I refer to as Twistor theory. Now, it's very much motivated by relativity facts and curious things like the nature of the celestial sphere. You think of the sky, that's a sphere. And the structure of that sky is what's called a conformal structure. And this is a thing I got interested in very early, that if you imagine two space travelers passing each other very close, and they look at the same sky, but they're traveling at almost very close to the speed of light, one with respect to the other. And they look up at the same sky, and there's a distortion of the sky they see. The stars are slightly different spots and so on. There's a thing called aberration, which has to do with the motion. But it has a very curious feature that it preserves angles. That is to say, if you imagined an angle in the sky of three stars close together and at a certain angle, that the other observer would see the same angle. So it's what the transformation of one observer to the sky to the other is what's called conformal. And this is a kind of geometry which I got very interested in, called conformal geometry. I mean, we know about Euclidean geometry, but that's to do with lengths. But this is to do with angles. And it's a much richer geometry. And the fact that it applies to the sky is an indication of something in a completely different subject. You might say the two big revolutions of 20th century physics. One is relativity, and here we see in special relativity. It doesn't work in Newtonian theory. Relativity, the conformal nature of the transformation of the sky. But the other is in quantum mechanics. And you have these complex numbers which are all intimately related to this conformal structure. And they play a big role when you think about spins of particles. And again, you get this same sphere, which is a conformal sphere, playing a fundamental role in physics. And this has to do with the complex numbers, which involve the square root of -1, sort of mysterious numbers, which are at the basis of quantum mechanics. And so I kind of thought of this as a link between relativity and quantum mechanics. And Twistor theory, I won't go into it here, but it's a mathematical formalism It has particular features. One of them is you have to have 3 space dimensions and 1 time dimension. So when I was being confronted with things like string theory, I quite liked the idea when strings were initially put forward, but when they seemed to consider you needed to have 26 dimensions of space-time or 10 dimensions or both together in some curious way, it didn't appeal to me at all, because the link between the quantum mechanics and relativity, which is through this conformal sphere, only works when you have 3 space dimensions and 1 time dimension. And so the theory which I developed, which I call Twistor theory, was based upon this very specific structure, and it doesn't work in other numbers of dimensions. Well, you can start doing it in other dimensions, it doesn't really work. And it took me years and years to try and make it work with general relativity, and only relatively recently did I see how these things fit together, and with quantum mechanics. And curious feature is that it needs to have, this was a big blow to me initially, the cosmological constant. See, this was this number introduced by Einstein in 1917 for the wrong reason. You see, he wanted a static universe. He liked a universe which was sort of spherical in space, sort of closed up on itself, and sort of sat there forever. And this was just about at the time when people were becoming convinced that the universe was expanding. But Einstein introduced this cosmological constant term, which we usually called it lambda, like a V upside down. And this was, as soon as he was convinced that the universe was actually expanding and this model doesn't work, he sort of retracted this cosmological term and regarded it as his greatest blunder. Now, you see, all the cosmology books were sort of, oh, Einstein says this number has to be there, and so they all consider the cosmological constant and so on. And I, sort of like everybody else, a lot of people thought, well, it shouldn't really be there. It's much nicer not having it there. And my trying to solve a big problem in Twistor theory, I thought I needed it to be 0. And I remember having this conversation with Jerry Oestreicher. And I was saying, do we really have to believe from these distant supernovae, they were observations of distant exploding stars, supernovae, that there seems to be evidence for this expansion, exponential expansion of the universe over and beyond the expansion that we already thought was consistent with the Einstein equations. And that seemed to indicate that there was this cosmological constant that Einstein had regarded as biggest blunder. It had to be there, it had to be positive. And I said to Jerry, I said, well, do we really have to believe that? I mean, because perhaps it's just dust out there, as many people said. And he looked at me and said, look, that's not the point. There are so many things in cosmology that are much better understood. They work so much better with this cosmological term. And I thought, okay, I'm prepared to give it up, what you say. So it was a good thing, because the later views that I had absolutely depend on having this cosmological constant. It has to be positive. It has to be there. We have to see this exponential expansion. And if it hadn't been for Jerry convincing me it was there, I'd have been still going down the wrong route that I was going down before.
No, I always say, Einstein's biggest blunder turned out to be that he called it a blunder.
Yes. Actually, well, I guess he wasn't right in the way he was using it.
That's right.
But it was it was a great insight, because it's basically the only thing you could do to his equations without wrecking them.
Yeah.
And he knew you could do that.
And he had great confidence in the equations.
Absolutely.
Especially after the 1919 the Eddington eclipse.
That's right.
So in the book, one thing that helped me as a young, scientifically, mathematically inclined young person when I read this in 1989 was the way that you very carefully lay out your opinions, but in a very even-handed fashion, as to different theories of math and physics, and you kind of give a rank ordering to them, which you talk about. And I want to revisit that on this, fifth decade.
I've forgotten all that.
Yes. So the categories I have them here are tentative, useful, and superb. And one of the most amazing things you do is you start off with Euclid, and you say Euclidean geometry is actually was in your characterization a physical theory, and I wonder if you can talk more about that. You seem to regard it as superb. As far as I mean. And it is superb, according to you. So can you comment on that?
How is it extraordinarily well? I mean, I guess it's an interesting question how the ancients looked at it. I mean, the ideas of Euclidean geometry was sort of based on angles and lengths and triangles, and sort of the view that a big triangle and a little triangle, the same geometry applied. If you had a really huge triangle, and if you added up its angles, it would still add up to 180 degrees. And people tried, there was a big activity where this, I'm forgetting his name now, this chap who tried to prove that the angles had to add up. I mean, Euclid realized that there was a puzzle here, that you needed to have a special assumption, which it was the parallel postulate, usually phrased in terms of if you have a line in a plane and a point in that plane which is not on the line, then there is only exactly one line, straight line, through that point which didn't meet the other line. And it was thought that somehow you should be able to deduce that from the others. I mean, it was a real insight for Euclid to see that that was an independent assumption.
Right.
And it took not just the ancients, but many people, and they tried to prove it. And Sakari and he spent his entire life trying to prove it, and at the end, more or less discovered what's called hyperbolic geometry. And there were other people who... what was his name?
Lobachevsky.
Lambert was somebody who proved beautiful theorems which had to depend on this other kind of geometry that people didn't think existed. And about how you add up the angles of a triangle and how much they fall short of 180 degrees as a measure of the angle of the triangle, area of the triangle. Right. An amazing thing. And how could you prove a thing like when you don't believe that there is any other geometry? Right. I don't know. I'm very interested to know what Lambert's psyche was here. I think he probably at certain times of his life thought there was that it was consistent to have different types of geometry, and other types he probably thought it was absurd. But you had to catch the times when he thought it was consistent, because he had this beautiful theorem in it. But then in Gauss, who more importantly tried to find, well, it's an interesting question, because he part of his job was to do geodesy. So he's actually measuring very big triangles.
The mountaintops.
And people are trying to think, oh, well, he's just doing geodesy. But I think at the back of his mind, he was really trying to see whether the geometry was Euclidean or not. Right. Because he knew that there were other kinds of geometry.
Right.
And it was really interesting how the history, people kind of toying with, were there other kinds of geometry? But the fact that Euclidean geometry is so precise, and it was sort of laid out as this wonderful theory, which it is, an amazing theory. And it lasted for goodness knows how many centuries before people, A, discovered there were other kinds of geometries, and B, with Einstein and, well, primarily Einstein, but realizing that you needed to, in order to describe a physics in which the principle of equivalence, that is, again, a lot of these ideas are ancient, but people didn't know quite what significance was. I mean, this was going back to Galileo. It's not just going back to Archimedes and going back to Euclid and people. But the fact that a gravitational field is equivalent to an acceleration. And so Galileo was extremely insightful. And you imagine, dropping these things from the
in a boat
tower or whatever it was, and they fall together, and they somehow you can cancel out gravity. And there's a wonderful description he has in one of his books where he talks about fireworks. And you see the fireworks and they explode, and you see these spheres, beautiful spheres, and they come and they fall, and they remain spheres.
Right.
And he pointed this out, and there was a deep insight in that. It's just as though there was no gravity, and the acceleration, if you're freely falling, it's as though there's no gravity. You
experience no
and
gravity.
That's a huge insight, which had to wait until Einstein to realize the importance of it.
Yeah, that's right. Yeah, that was in the Discorsi, I think, the last book that Galileo wrote.
Yes.
So I want to read from Emperor's New Mind, a paragraph that speaks to me to this very day, and I remember being moved by it way back when. He said, "Great works of art are indeed closer to God than our lesser ones. It is a feeling not uncommon amongst artists, that in their greatest works they are revealing eternal truths, which have some kind of prior ethereal existence, while their lesser works may be more arbitrary, of nature more mortal constructions. Likewise, an engineering innovation with a beautiful economy where a great deal is achieved in the scope of the application of some simple, unexpected idea, might appropriately be described as a discovery rather than an invention. Now, this harkens back to whether or not mathematical truths are in
Yes.
some way discovered or invented.
Yes, indeed.
And I wonder if you can weigh in with your vast experience, gleaned both before and after this book. And where do you fall now?
Well, certainly I haven't changed my view in that particular respect. I have in certain others. Yeah, I think the mathematics, well, it's a Platonic view, you would say, that the mathematics has its own world. You see, I like to do this with an illustration, which I think first had in Shadows of the Mind, where I had three types of existence, in a sense. And if you're a mathematician, you very strongly get the feeling that it's like a bit like geology or archaeology or something. You're exploring a world out there. You're
Unknown
discovering things which are out there. You don't invent the theorems. You discover truths which are in some sense out there in a world, but it's not the world, the physical world, because the things you find, then, you know, you try to draw a triangle and it's not quite. And how do you draw a straight line when the more you know about the nature of matter, you see it's granular in certain respects?
Yeah, you're talking here about what is the number 3? Is it?
Yes.
Very difficult.
And so when you think about the mathematics, you really have to think about it in this Platonic way. It's not that you're creating it. I mean, you sometimes do things which are simply sufficiently wild that they look as though you've made it all up. But in a certain sense, if it really works beautifully, there's something out there which is out of your control, and it's much more like exploration. You could say this is a feeling that one has, but it's more, I think, strong. You see, this is one of the worlds, the world, the Platonic world of mathematics, which I sort of draw as this sphere at the top of the picture. And then a little bit of that world, and it's only a very tiny bit, because if you look at any article or any journal of pure mathematics, and you will see the articles in there which have any relevance whatsoever to the physical world. Very, very tiny.
Yeah, and they might not even have a number in it. Right?
It's even a number.
Pure symbolic.
That's right, and it's a very tiny bit of it, which sometimes it turns out later things that you find, well and behold, this beautiful theorem which was in that pure mathematical work, and now it's found an application. So you see that. But when you think of the whole totality of the mathematical work that's been done, that's explored, if you like, it's a really tiny part of that world, a very productive, magical, particularly magical part of that world, which seems to be, and I have it sort of projecting out to the physical world. The laws that we see being extraordinarily precise. Well, I say Euclidean geometry is, even though we know now not exactly mirrored in the geometry of the physical world, it's a basic ingredient of everything we think about in geometry. So it has a huge impact into physics. But then the more we learn about physics, it's governed by equations and geometrical ideas and things, and we reduce them to mathematics. And in that mathematics, we can gain enormous precision in the way we describe and understand the way the physical world operates. Now, this is in some sense, the view we have, and this is the view I have, is that this small part of the mathematical world encompasses, in a certain sense, the whole of the physical world. So I draw this in this rather strange way. A little tiny part of the world, the mathematical world, seems to encompass the behavior of this physical world. It seems to be, when we get our laws right, they really be almost as though we reduce them to mathematics. You might say, well, what is a rock? Well, this rock is made of molecules and things like that. And what are the molecules made of? Well, they're made of atoms. What are the atoms made of? Well, they're made of fundamental particles, electrons, and you worry about the neutrons and protons and then the gluons and things. What are they? You say, well, what sticks the particles together? Are they particles themselves? Well, then you worry about the photons. Well, you have these as, they used to be fields, and then you see they're particles. But then you say, what is an electron? Well, the best you can do is it's a solution of the Dirac equation. You say, well, that's a pretty abstract notion. And you kind of have to resort to mathematics when you try to probe reality at its deepest levels. And then there's the next question, you see, which is my third world, which is the world of conscious experience. And so the type of view I'm expressing, well, both in The Emperor's New Mind and Shadows of the Mind, more explicitly in this picture, is that there's a third world, which is the world of conscious experience. Some people take that as primary, and they try to build everything else out of that. I think that's a pretty hopeless task, because our sensory experiences are very hard to describe any of these other things in a precise way. But nevertheless, that's one. You can have different ways of looking at it. But again, it seems to be a very small part of the world of physics which is actually supports consciousness. So, okay, human beings, sure. I think it extends much more broadly than that. And animals, maybe many animals, whether not all animals, I wouldn't know. But certainly, I think the difference between human beings and certain animals is, okay, great in certain respects, but not fundamental. I just think that people who are dog owners, for example, are pretty convinced their dogs are conscious. I think octopuses are conscious. Elephants, I would pretty way down though below that. I think mice are conscious too. I used to have infestations of mice in the place I used to live in, and I'd admire the cleverness of these little creatures sometimes. How they could step over the trap that way, quite deliberately, and take out all the food
and
completely cleaned out, and they hadn't touched the thing which would trip them out. I just have a great admiration for the mice. So there's something which goes deep down into the world. But it's still a tiny part of this physical world,
In the Penrose hierarchy of superb, useful, and tentative, where do you rank? Because obviously geometry is superb, and obviously mathematics is superb.
Well, mathematics is, I would say, you have to spread it out of all the other theories.
Sure.
So it's not just mathematics in itself.
But do you feel, in principle, a theory of consciousness could be superb? Is it possible for it to be superb, or is it only possible for it to be useful?
I think if we get it right, we're a long way from it.
What would it look like? What would such a theory look like?
Faintest idea. All I can say about it in the studies of the books I've written is a little chip, I would say. And the tiny thing I'm trying to say is that consciousness, well, again, it's a little part. Consciousness in so all sorts of things, pain and perception of the color blue, and happiness and love and all sorts of things. I don't talk about most of those things in my book. I just talk about the one thing that I could say anything about, which is understanding. And I concentrate on that because there are these theorems of logic, most particularly Gödel's theorem and Turing's analysis of it in terms of computation, the ideas of computation and so on, lead me to believe that human understanding is not computable. It's not a computation. And a lot of people, that's where a lot of people argued with me, because somehow it tells us that an algorithm, you see, we have these wonderful computers and what they can do, and they do incredible things, I agree with that. But they run on algorithms. And this is what we understand, this notion of an algorithm, which was, well, it really goes back to what was Arabic algorithmy, but that was Turing and a few other people, Post and Church and people, who really made clear the idea of what an algorithm is, what a computation is. And the Gödel theorem tells you that our understanding is not a computation. I mean, this is a story which is, a lot of people complain about, but I think the argument is pretty clear that what we do when we understand a proof in mathematics is not following an algorithm. And it's very clear because of the Gödel thing, which says what do you mean by a proof? You see, well, a proof is using certain kinds of rules, and you have to use them correctly. And if you really think of it as a proof, you've got to believe that those rules only give you true statements. Now, it's that thing, the belief that it only gives you true statements, which enables you to demonstrate the truth of a proposition, which Gödel produces very ingeniously, a proposition which you can see must be true, Nevertheless, it cannot be derived by means of whatever rules you start with.
Right,
As long as you believe those rules only give you truths,
Mhm.
then you must believe this Gödel statement is also true and not derivable by means of those rules. Now, when I learnt that, I was stunned by it. You see, it wasn't that you can prove certain things can't be derived in certain ways. It's much stronger than that. It's saying whatever procedure you use, if it's following definite rules,
Algorithm.
which you believe in, which you
Mhm.
trust, the
Mhm.
algorithm which you trust, then you can see how to transcend that. Now, what is it in our abilities to think, perceive, conscious perception that transcends computation?
Mm.
Oh, there are lots of arguments people present, and one of these is, well, you know, the algorithm we use in our heads is so complicated that we'll never be able to see what the Gödel thing is. Well, yeah, sure. But the point is that how did it come about? By natural selection. It has to have been by relatively simple things, which we can certainly understand. These very complicated things which you can maybe have a computer which could do things which are pretty hard to see why they're true because it's very, very elaborate. That's not what was naturally selected for. What was naturally selected for was this more basic principle of an understanding. And that is not a computation. It's something, I don't know what it is. Don't ask me what it is.
No.
That's the
So you're
real
distinguishing
challenge.
between
Yes.
computability and actual comprehension. And
It's the comprehension of why the algorithm does what it's supposed to do.
Mhm.
And it's not simply trying this and that, zillion
Right.
of times.
Inductively.
In a certain sense, I mean, there's an irony here because, okay, conscious beings came about in a way by natural selections, and
Which is an
it wasn't
algorithmic, right?
some way of picking out the ones that were more successful. But they were successful, in the view I hold, by probing the laws of physics at a much deeper level than we've seen yet,
Mhm.
at this level where we see non-computable action.
Mm.
And this has to be still it was already the argument I gave in the Emperor's New Mind, but although not quite the right criterion in my view, it has to be at this place where we have to go beyond current quantum theory. And the argument came about, which is what I formulated the view basically when I was I think it was my first year as a graduate student, when I went to courses by a man called Steen on mathematical logic, Bondi on general relativity, and Dirac, a great quantum physicist, on quantum mechanics. And I tried to see what in the physical world can be not put on a computer, basically. And basically, my conclusion was it was this curious feature of quantum mechanics where you have an inconsistency. It's basically making a measurement. You see, quantum theory consists of two parts. One is following an equation, the Schrödinger equation. And that's a thing you can put on a computer.
Unitary evolution.
Unitary evolution.
Smooth.
And the other is where you don't do unitary evolution. You make a measurement, you collapse the wave function, and you cheat. But you have to do that to have the world we see. And so this seemed to me that's the place where the non-computable physics has to come in. I don't see in detail how it comes in. And it's a big mystery. But my claim is you've got to harness that bit, and that somehow the conscious brain is at some point making use of this part of this place. It's not just that it uses quantum mechanics. Many people poo-poo that already. They say, oh, no, it's classical physics. Oh, you don't know what quantum mechanics. No, but we see that's wrong already, because in things like photosynthesis and maybe bird migration, there are other places where we seem to see effects which do depend crucially on quantum effects. Well, chemistry is already quantum, but these are things a little bit outside that.
Saying like room temperature, short coherence length.
Preserving of quantum coherence at room temperature. So, sure, the argument is nature has found a way to do it. Deep in the brain, and much more likely it'll be to do with microtubules, and probably how they relate to other structures. And
so anything with a microtubule could participate in quantum mechanical measurement?
Maybe, even it doesn't say that much. I mean, there are these two structures, the A lattice and the B lattice. The A lattice is very symmetrical. The B lattice is not so symmetrical. The B lattice is still symmetrical, but not so much. And most microtubules in the body all over the place tend to be B lattice. the A-lattice ones seem to be much more promising for doing things in the brain probably, and maybe conscious actions. So the guess is that whatever is really responsible for conscious action is not just microtubules, but A-lattice microtubules. And there is some theoretical work done by various people which does seem to indicate that.
Mm-hmm.
That's certainly for the future. And I think that's way ahead of what we have at the moment.
Are there models, mice or octopi, or are we able to test in living structures that these things can occur? I mean, Schrodinger cat experiment supervised by an octopus or something that the folks at PETA won't
well,
object
I think
to.
going to that level is unlikely for a while, for a long term. I think it's much more likely probing areas of the brain, not so much areas of the brain, but exactly what's going on when. And there are things, it's outside my area of expertise, but there are sort of waves of activity involving different layers in the brain. And where the conscious activity seems to come in is where there are large numbers of these certain kinds of cells called pyramidal cells. I don't know enough about it to know exactly. There is a big question, you see, which people often raise, and that is, there are far more cells, neurons. I only recently learned it's more. I knew it was comparable.
Yeah.
In this part of the brain called the cerebellum.
Mm-hmm.
Now, the cerebellum is not the people you think of. It's just part of the top with all its convolutions and all that. It's a part which looks much more like a ball of knitting. Underneath and at the back, it has more neurons, considerably more than there are in the, and more connections between neurons. And it seems to be pretty well unconscious. It's activated when you do very precise motions. If you become an expert tennis player or play the piano beautifully well, you don't think every moment, where do I put my middle finger in exactly what spot? That's controlled pretty well by unconscious actions. And the precision needed in these actions are carried out by the cerebellum. I mean, initially you have to learn about them in the cerebrum part, but when they become unconscious, controlled with such unconscious precision that you need at these great levels of expertise, or even when you're walking down the street probably, certainly when you're driving the car not thinking about it, it's probably controlled by the cerebellum. Now, that doesn't seem to be conscious.
Right.
What's the difference? Well, I don't know, but Stewart will say there are no pyramidal cells in the cerebellum, and the pyramidal cells have many more microtubules in them, and they're organized in a different way from those in the cerebellum. That's the kind of thing one could explore more and see to what extent is it that these structures with more microtubules and more A-lattice microtubules maybe actually seem to be more concerned with conscious thinking. And it's definitely true that some parts of the brain are much, much more to do with consciousness than others. Well, that's certainly true with the cerebellum. I don't know what the question is with other parts of the cerebrum.
And on a practical level, I'm curious to get your perspective on recent developments in things like quantum computing. You very presciently talked in this book about not only chess, and this is before Deep Blue it defeated Garry Kasparov, but you talked about the game Go, which was recently Google's version of the Go playing algorithm beat it, the best human being. You talked about all these things in the late 80s. It's really amusing to look back. The other things you talked about, quantum teleportation. There's a charming chapter where you talk about taking the molecules of a brick and replacing them, and is it the same brick? And then you say, well, what's the difference in the brick in your brain? And could you do these things to this? So I'm interested with all the technological developments in quantum computing that we've recently achieved, quantum supremacy and things like that. What's your from the standpoint of the long view of history, how important is this era in modern times? How will you feel like it will be regarded in the future? Was this a critical time, or is it?
It's very hard for me to judge at the moment. I mean, certainly the quantum computers that they have now, and they've made a lot of progress, are not like the ones that were being considered before, where you might have something like a classical computer, but then you sort of introduced quantum superpositions of calculations and so on. They're basically a different kind of structure, and they're not, as far as I know, really universal machines. See, one of them wonderful things about ordinary computers, if I can call them ordinary, is that depending on this notion developed by Turing and Church and Post and Gödel and people of computability being a universal concept. So you can build up through very simple ingredients a machine which can in principle do any computation. Now these ideas are developed into, of course, lots of ingenious ideas go into it, but the modern computers are basically universal computing machines. So any kind of algorithm you can put on the computer. Now with the quantum machines, it's really a very small number of problems. Okay, they're very specific ones that they can do very well.
Simulate Hamiltonians
as far as I'm aware, they're not really general purpose machines. So it's not really quite at that level. Maybe they will become, and maybe there will be a point. You see, I sometimes comment on this. See, in the old days, people used to say, well, you get better computers. This is before the quantum computers. You get better machines the smaller you make them. So you can get smaller and smaller chips, and then they become smaller and smaller and smaller, and they're much more effective, and you get more power out of the machine. And then there's a certain limit, because at a certain point you run into the problems of quantum mechanics. So they would say the quantum limit, you see, that'll stick us up at some point. Well, then, of course, people say, no, well, once you know what's going on at the quantum level, you can actually harness the quantum level. And so you have this idea of a quantum computer, which enables you to transcend, at least to some degree, what you can do with a classical machine. And so maybe something similar might come later on, where people say, well, there's a certain level, a limit to what you can do with your quantum machines, because if you have too much mass moving around, then you're going to run into the limit where the quantum mechanics doesn't hold, and you've got to go beyond it, and so there will be a limit there, the state reduction limit of quantum computers. And then maybe somebody say, well, we've got maybe by then some great theory which tells you, which goes beyond standard quantum mechanics, and then maybe you can construct a device which goes beyond it by taking advantage of this theory. I think I'm glad I won't be alive by then, because I think if these things do come about, I'm a little bit worried about what may be done with them.
Yeah, I wish you a long life. I wish that that's the only thing I disagree with you. I don't want you to leave the mortal coil too soon, because I want to see. And actually, that segues maybe perhaps to my final question, which has to do with all these various novel ideas that you've had, and perhaps certainly no other modern physicist has had contributions as diverse as cosmology, as consciousness, as Twistor theory, as talking computation and artificial intelligence. If you could ask, as Einstein used to call him, the old one, God, if you could get the answer to one of these, many topics that you've researched, throughout your life, throughout your very productive career, which is the thing that most fascinates you? Which is the thing that most captivates your imagination?
Well, you see, it's a difficult question, because at the moment, the thing which excites me most is the cosmology. But there, you see, it excites me because, you see, I have a certain wild idea, which I think may well be true, and most standard cosmologists don't believe me, you see. Okay. But there are bits of evidence we're beginning to see which do suggest that maybe there is some truth in this model. You're speaking about just for the listeners, you're speaking about the conformal cyclic model, which says that the Big Bang was not really the beginning. It was the conformal continuation. I talked about the conformal geometry, where big and small you're not interested in, you're interested in size. But what I'm trying to say is, in the Big Bang, because the energies are so big and the particles become effectively massless, they can't tell big from small. So at that stage, there's the kind of geometry doesn't know big from small is important. The other place when you can't tell big from small is an extremely remote future, where the universe expands and expands exponentially, and you mostly photons running around, and they don't know big from small. And you've got the black holes, and then they eventually evaporate away by Hawking evaporation, and then you've got nothing left. It's not quite true. You have to be a little careful about that. But roughly speaking, the idea is that this very remote future, it doesn't know big from small either. So the crazy idea is that this very remote future joins on to the Big Bang of a next eon. And our Big Bang was the conformally squashed remote future of a previous eon. Now, it's a completely wild idea because one tends to think, well, why, how does this very stretched out, very rarefied, very cold, infinite remote future of an eon simply become the very concentrated, extremely hot and dense next Big Bang?
Right.
Well, the thing is, because the geometry there is the conformal one, the big and smaller equivalent. Okay, it takes people a lot of convincing to make sure that they believe this. But the claim is that we're making is that there are certain signals which do get through. And the first ones we're thinking were supermassive black holes running into each other and producing huge bursts of gravitational radiation, which would give you signals which could get through. And we claim that there are such indications. Much stronger are the more recent observations. This is different, so one mustn't get them confused. The link between the two is supermassive black holes. But now, this is the black holes in the very remote future, basically swallowed up in an entire cluster of galaxies, and the entire, pretty well, most of the mass in that cluster of galaxies will get swallowed by the black hole. It sits around, and eventually evaporates away by Hawking evaporation into photons. You see, I used to think it's a very boring phase of the universe when you've got nothing but black holes left. What's really boring is when they've all evaporated away. And so I was worrying about this unbelievably boring universe. And then I began to think, well, who's going to be bored by it?
Yeah, exactly. That's
Only the
eternity is a pretty long time.
That's right. It's an awful long time, especially at the end, as Woody Allen said. But the main point here is that photons don't experience eternity because they've got no mass.
No clocks. Yeah, there's no clocks. Right?
Yeah, they don't have clocks. So that infinity is no big deal to a photon. It just zips through into the next eon. And that's the view I had, and tried to make it into a theory. And these Hawking points, which are the splodges, I would say, maybe a Hawking splodge. But it's pretty circular, it would be. There would be spots in the sky about 8 times the diameter of the full moon.
Right.
And you wouldn't see them any bigger than that. That's definitely a prediction of the theory. Occasionally a bit smaller, but they would be slightly raised temperature. And I don't know, this is my suggestion, that if you had a planetarium, usually you see stars and planets and things like that, have the microwave background on your planetarium with enough detail that I guess the Planck satellite would reveal, and you look it up at it and you would see them. I'd like to know if that's true.
Well, we have a beach ball behind you, which will
which
could demonstrate
I'll
high resolution. That's right.
You need a bit more resolution than that.
Yes,
because
right,
I think the little spot 8 times the moon diameter would look like a pinprick in that model. So it needs to be a bit bigger than that. But the intensity overall is about 15 times the average increased temperatures that you see. So the normal variations in temperature are 10 to the minus 5, and here you're looking at about 10 to the minus 4. A little bit more of an intensity, but probably not too obvious unless, I don't know, I would expect, you look at that in the sky and you'd see them. I'd like to know. I'd like to have a good, well-done planetarium, and I'd like to sit in it and see whether you can see them.
Well, you and I both had the pleasure at one point or another of speaking at the Hayden Planetarium. And when I spoke there, they were kind enough to project onto the dome the CMB map as revealed from the Planck satellite. So maybe we can do that. They did do it. So maybe we can arrange it for your next visit to New York City.
I'd love to see. Yeah.
It's really just a startling. It's almost induced vertigo in me, which was to be centered on this universe that I'd spent so much time studying.
I would love to see that.
Yeah, it's quite beautiful.
Well, you said I'd know where to look for some of them, the 5 most prominent spots.
Right.
I suppose. But it's intriguing to know whether you would really see them with the naked eye or not. Well, naked eye with looking at microwave
processing,
radiation. But that you were asking me what...
Yeah.
I mean, that's what excites me most at the moment, because that's ongoing, and you can really see, does this conform to... Does the theory conform to the observations or not? The next thing I would say would be the state reduction experiments, which are a little way off, but not that long. There are experiments currently being done which within the next 3 years maybe we'll get an answer. There are other experiments. The one I'm thinking of are the ones by Dirk Baumeester, and this is his estimate, and he's been pretty accurate in predicting how long his things will be. So I think he may have an answer. Of course, the answer may go the wrong way as far as I'm concerned, but I hope he will see state reduction. That's a sort of deviation from standard quantum mechanics.
Right.
Of course, since it's a deviation, a lot of people will complain and say that's a bad experiment, it's due to decoherence and all that, so he'll have to persuade them that it's a good experiment. But there are other experiments using Bose-Einstein condensates. I think they're probably the next, maybe they will see effects.
Right.
I have a colleague in Nottingham, Yvette Fuentes, who has proposals which I hope will be performed experimental. They haven't been set up yet. And the third thing is consciousness. There, you see, I think we're a lot longer. I think we may see the effects in the not biological experiments, but just the physics experiments are being done now. Whether you will see the quantum effects in microtubules or what, quite possibly. I think some general evidence for quantum coherence in biological systems might not be too long from now, but to see any direct evidence of connections with consciousness, I think is a long way off, because it's really such a slippery subject.
Right.
To get hold of that in an experimental way may be really tricky, but maybe.
Well, if Emperor's New Mind, which is still relevant now in its 5th decade after publication, is any guide, it's surely to be expected that we'll have various new insights into these fascinating subjects that you've worked on. And I can't tell you how much we appreciate you here. Your graciousness, as always, in visiting us and sharing your ideas and opinions with us are really very much appreciated. So thank you, Sir Roger, for your visit. And we look forward to many years of continued success.
Well, thank you very much. And I'm very excited to see how these experiments and the telescope in Chile and all that will come along. It really sounds like a very exciting project.
Thank you very much.
The only thing we can be sure of about the future is that it will be absolutely fantastic.
5, 4, 3, 2,